Welcome to antenna as a component. Today we are going to speak the concept of isotropic antenna followed by the definition of directive gain. The purpose of this slide is to study about the isotropic antenna and how it radiates. And then we will use this concept to define the directive gain. An isotropic antenna is known also as a point source. It radiates the power equally in all directions, and its radiation appears as a sphere in the free space with the isotropic antenna or the point source as the center of the sphere. This is how it looks like, just a sphere around the point source. We need to know that it is just a mathematical concept. It does not exist in nature, and we use it as a reference to other antennas, as we will know. Let's review one item which we have already studied in the previous video, the power density. And we studied that the power or the total power is equal to double integral of the power density dA. But in case of the isotropic antenna, we have a constant power density across all angles. Then this is just a constant, so we take it out from the integration, and then we make double integral of the dA, the unit area, which will result in by r squared multiplied by 4. Then we just reformulate this, and we can reach that the power density, which is a constant of an antenna, or specifically isotropic antenna, is calculated as bt over pi r squared multiplied by 4. Likewise, we have also studied the power intensity. For isotropic antenna, if you follow the analysis here, you will get a similar result, which is the power density of the power intensity of an isotropic antenna is equal to bt divided by 4 pi, which is the unit solid angle. Now we will learn about one of the most important concepts in antenna analysis, which is directive gain. So what's an directive gain? It is the ratio between the power density of an antenna to the power density of an isotropic antenna. So in mathematical form, G equal to BD over PD of an isotropic, and we have learned in the previous video that BD isotropic is just equal to BT over 4 pi r squared, and the total power also is equal to double integral of the power density dA. So taking these two equations, substituting the gain equation, then we can reach this formula, very famous formula in gain calculation, which is just equal to 4 by r squared multiplied the power density of the antenna divided by the double integral of the power density of the same antenna. And actually we can do the same thing if we have the power intensity. As we know, power intensity equal to a power density divided by r squared, and then if you reformulate your equations here, you can get G equal to U over U isotropic, and also you can reach the equation that G is equal to 4 by U divided by double integral of U, but here in terms of the omega. Now, before concluding, we have some key parameters of the isotropic antenna, which are directive gain and effective aperture area. The directive gain is unity, and if you take the logarithmic form, it will be 0 dBi. We will learn in detail how to calculate this one. But why it is unity? Because by definition, G is actually just power density divided by the power density of isotropic. So if you want to get G isotropic, it should be equal to what? B d isotropic again divided by itself, which will be by definition equal to 1, because this cancel each other. And if you took the log, because G is equal to 10 log to the 10 reference base of 1, which is equal to 0. But what is matter here is actually the why we used dBi, not just dB here. Why dBi? Unit actually is just dB because you are taking the logarithm. So this is the correct unit. But since we are referring to an isotropic, then we put a hint here that we are comparing to isotropic, because in reality the antenna is a passive component and doesn't have a gain, and its gain is just a relative gain. If you have put an some power in an isotropic antenna, it will radiate in all directions. It will assume that we are a planar universe, so your isotropic antenna radiation will be with the same value in all directions. But if you have another antenna which is not isotropic, let's say directive antenna, and assume we are in the same planar universe, and you have the same power and radiated, say, in this XY, for example, radiated only in this direction. So what will happen is that this area should be the same as the area of the isotrope, because it's same power, right? If you integrate, it should be the same. So this means that if you compare the gain in this specific point at the x-axis, the relative value between the directive antenna and isotropic is how much in dB, and since it's compared value, then we add the I. Now with the other quantity, we have the effective aperture area defined as lambda square over 4 pi, and the reason is that we have a unity gain of the isotropic antenna, because the original equation actually is that the effective aperture area is equal to the gain multiplied by lambda square over 4 pi, and if you have a unity gain, this will reduce only to the lambda square over 4 pi, and we have a separate video for this specific definition, I mean the effective aperture area. Now we are with the takeaway from this lecture. We have defined the directive gain as either the ratio between the power density of an antenna and the same quantity for isotropic, or the power intensity of an antenna and the power intensity of an isotropic, and it can be reformulated in terms of the power density of this specific antenna or the power intensity of the same antenna. And we have learned also about the reference antenna or the isotropic antenna or the point source, and we have learned that its power density and power intensity are constants and can be calculated as the total power available divided by the area of the sphere, or the surface area of the sphere, 4 by r squared, or the solid angle of an total solid angle of an sphere, which is 4 pi in case of power intensity. And we have learned also that its gain is just 0 dBi. Stay tuned for more concept in antenna as component.